so this is a paper that the paper gives an algorithm that can take any image of a person. It can either be like a painting or an image of an actual person, and it outputs a video of that person talking. So as you might imagine, it got a lot of publicity, a lot of people talking about it. This was researched on a Samsung AI Center in Moscow. Okay, so let me first just break down what the title actually means, because there's a lot of keywords in the title. So view shot, that means this paradigm in machine learning where you train on a big training set, and then at testing time you just get like a few images of a person, and the algorithm needs to output something just based on these few images. And then adversarial learning, that means that this algorithm will make use of a very popular framework called generative adversarial networks. Realistic, so the output images have very high realism scores. They look very realistic. Neural, that means neural networks. And then talking heads, so not the band, but it outputs videos of people talking. Okay. So I'll just give a quick overview of the algorithm and then get into background, related work, and the details of the algorithm. So this algorithm is trained on a massive data set of YouTube interviews. So there's like 2,000 hours plus of interviews in this data set called Voxlab2. And then the input to the algorithm, say it was trained on a bunch of interviews, but then I give it a new person, like Donald Trump, and it's never seen Trump before. And I also give it a video of myself saying, I want to raise taxes. So then the output will be Donald Trump saying, I want to raise taxes. Okay. Just an idea of the algorithm, it uses 3 neural networks. So there's embedder, generator, and discriminator. So this is just more of a demo of the algorithm. So they released this YouTube video of showing the power of their algorithm. So here they give it images of a person and also like a landmark of a face talking, and then the output is that person talking. It can also, like if you only give it images of a person head on, then it can still output like the person turned to the side. So I guess the algorithm learns a lot about like faces, and it's able to generalize to all these other images. So you might ask, like, what are the applications of this stuff? So in the paper, they mentioned telepresence, like video conferencing or video games, and also in the special effects industry. There might also be like a lot of ethical questions behind this type of work. So the paper did not mention this stuff. A lot of people online mentioned a lot of other applications. And as of right now, there's no code or pre-trained models online. Okay, so I gave a quick overview. Now I'm going to go through a little bit of background on deep learning and GANs, so we're all on the same page. And then there is research going on throughout the 90s. And then when machine learning got big in the 2000s, neural networks were still trailing behind a little bit. There's like a folklore quote that says neural networks are the second best way to do almost anything. But then all of this changed right around 2012 when a lot of people say the big deep learning revolution happened at this yearly ImageNet competition. So that there's this competition where there's this data set of 1 million images and 100 classes. And in 2012, this team released a deep learning algorithm that just blew away all the other algorithms. It got like more than 10% accuracy improved from the second best algorithm. So this is when everyone was like, okay, deep learning might be like a really powerful tool. So what is deep learning? So again, I'll just give a quick refresher of the whole model. So say we want to do some task like classify photos of flowers or photos of elephants. So what we would do is give our algorithm a bunch of training data. So we have a bunch of images images of flowers and elephants, and we say, this is a flower, this is an elephant. And then at training time, the algorithm does a lot of computation, and then once the algorithm's done training, we can give it new images, and it'll be able to correctly predict whether it's a flower or an elephant. And so what does it do during the training time? So neural networks consist of a bunch of these neurons, and they all have inputs. And so the neurons in the first layer, they take the pixels of the image as input, and then there's some activation function where the neuron is activated at some weighted sum of its inputs, sum of its value. And then in the middle layers, the inputs of the neurons are neurons from the previous layer. So basically, you can think of it as just this really complicated function with a bunch of parameters. And at the start, we just set all the parameters to random values, so the algorithm does very badly. But then once we give it a bunch of training data, it'll try to predict, like, oh, is this an elephant? And we'll say, no, that's a flower. So then it'll update its weights a little bit. And if we give it a bunch of computation time and a bunch of data, eventually it'll become really good at classifying all these different images. So this is just a really high-level overview of deep learning. There's like a lot more that goes into it, but this is sort of like a background. Any questions so far, Ryan? Okay, so next I'll talk about a very popular type of deep learning algorithm called generative adversarial networks. So this was introduced by Ian Goodfellow in 2014. And I think Jan LeCun, who's like a very famous deep learning researcher, said this was maybe the most important discovery in the last decade in deep learning. So it's a really interesting algorithm framework. And so the idea is that, if you remember from the last slide, we had a deep learning algorithm that could classify different photos as either an elephant or a flower. But this neural network can actually generate new images. So if you look at these photos of people in the bottom left, these are actually generated by an AI algorithm. These people do not exist. So this is an algorithm that can actually do that. So the adversarial, that means that there are these two deep networks within this algorithm framework. There's a generator and a discriminator, and they're kind of like fighting against each other at training time. So we say it's a generative adversarial network. So the goal of the generator is to output these realistic looking images, and the goal of the discriminator is to classify it. So it gets examples of real images and also fake images from the generator, and it tries to tell them apart. It tries to say, that's fake, that's real. And so at the start, both of these networks are really bad, but then if we give them a bunch of data and a bunch of time to train, eventually both of them will start getting better and better at training. And they're sort of, the entire time, they're sort of fighting against each other. Like, the generator is trying to fool the discriminator, and the discriminator is trying to kind of keep classifying, like, call out the generator, like, that's fake. So yeah, at the very end of the training, we can just chop off the discriminator and only use the generator to just generate new images of whatever we want, faces or whatever's in our training set. Okay. So now I'll talk a little bit about related work for these talking head models. So first, these make use of the meta-learning framework. That's where we say we only train our algorithm on flowers or elephants, but then at testing time, we give it new images of tigers. And we only give it like a couple images of tigers, and then it has to generate new images of tigers, even though it mostly trained on just flowers and elephants. So there's a lot of work on meta learning. And then just in the past year, there have been a few papers on talking heads models. So there's this X2 face and also Pix2Pix HD that also try to output talking heads. So these are also great papers. But the paper I'm talking about today, it got really good scores just from a single image. So these works didn't do quite as well when you just give it like single, like only a few images for the input. Okay, and I just want to say this is like a very hard problem because humans are really good at telling the difference between what's a face and what's almost a face but not quite a face. So we're really good at like spotting that difference. And this is called the uncanny valley effect. So it's like children's dolls are over here, where like they're fine for us, they're like sort of human but not. But then when things like really close to humans but not quite, we're able to like really tell the difference. Okay, so basically the algorithms need to do really well, otherwise we'll easily be able to say that that's fake. Okay, so I'm about to start talking about the actual algorithm of the paper, but one more slide on background. So the algorithm makes use of face alignment, and this is just where we try to like map a person's face in a video. And this was a really hard task like 5 or 7 years ago, but nowadays using deep learning, it's like a fairly simple thing. You can just like download an app that'll do this. So there are a bunch of algorithms now that can map out the face of a person. Okay, so now I'll start talking about the actual algorithm of the paper. So this is a slide from their paper, the entire framework. Like I said earlier, there are 3 neural networks, the generator, embedder, and discriminator. So let me break this down a little bit. The job for each of the neural networks. So the embedder's job is it gets as input the video frame and also the landmarks. So right here, these are the landmarks. That's what I was talking about on the last slide, like the orientation of the face. So we just give it this information, and then the embedder's job is to output information about the specific person. So if we give it a video of my head, it'll try to output some features that are like what it means to be Colin. And this should be invariant of whether like my face is like that or like that. It'll just try to like learn like the person's specific information. Okay. And then the generator takes as input the landmark, so the orientation of the face that we want it to be in. And then it'll also take in as input the information about the person, and it'll try to output the person in that orientation. Okay. So the generator and the embedder sort of work together, where the embedder like compresses information about the person, and the generator then takes it. Actually, we use the output from the embedder to sort of tune the parameters of the generator, so the generator can easily output a photo of that person in that orientation. Okay. And now the discriminator takes in the actual image and the predicted image from the generator, and it tries to tell the difference, and it tries to say how realistic is this image. Okay, so the way this works at training time is remember we have this huge data set of video, so we give the algorithm like we take a 10-second video and we cut off the last second. So then we give the generator, the embedder, the first 9 seconds, and then tell them, try to predict the last second of the video. And so then the generator will like have its second, and then we also have access to like the actual truth, like the actual end of the video. And so then the discriminator will like try to tell them the correct. Okay. And so it's 3 neural networks, but then we also need a neural network to do the landmarks, and we also, so I'll talk about this in the next slide, but there's also another neural network. So this entire algorithm is sort of like built up on a bunch of neural networks and a bunch of prior work.
Question for you.
Yep.
So what kind of things does the embedder, like, can you give an example of the things that the embedder is embedding? Like, because you're giving it the landmarks already, so like, what else would it be learning or embedding, you know?
Yeah, so the goal of the embedder is to just sort of compress the idea of like every individual person. We don't really know, like we know that it does that job very well, but we can't like quantify exactly how it's doing that. This is like the mystery of neural networks. It's very hard to look inside them and say, oh, like it encoded like that I'm a male and that like my race and like my like eye color. It's very mysterious to us, but it should be doing things sort of like this. Like you might think of it as encoding like race and gender and eye color and stuff.
Yeah, I was curious about how the embedding is used to modulate parameters in the generator. Like you could just take like the embedding and concatenate it with the generator input or something like that. But like, if you could shed some light on that.
Yeah, so I guess the output of the embedder is used to like jumpstart the weights in the generator. So some of the weights. So they're actually split up. Like the generator has weights for the specific person and also weights for the orientation. And so the output of the embedder goes to the weights like specifically for that person. So the generator and the embedder, their loss function is so basically we need this trade-off between how realistic the face looks and also how well does the output match the actual person it's trying to output. So for instance, if we only give the loss for the generator as the realism score, then it could output just a photo of anybody that's very realistic. So we need it to sort of have a loss for both of these terms. So the generator loss is the concept loss and also the output of the discriminator, which is like how, so the adversarial term is like how realistic it is. And then the content loss, that's, if I go back to the last slide. So the content loss is how different the synthesized image is from the ground truth. And to do that, we actually use another neural network, which is trained on face recognition. So there's a bunch of like out-of-the-box facial recognition software too. So yeah, in all I guess it's like 5 neural networks, although just 3 are trained together, the other 2 are just used like already trained out of the box. Okay. There's also this extra term called embedding loss. This is something I was like trying to decide if I should sweep this detail under the rug or not, but if you guys are curious, so there's like this new technique recently for GANs where the discriminator is also used as an embedder, and so now there are 2 embedders, and then it makes training more stable if the discriminator has an embedder, and we add a loss term where how close both of these embedders are. This is just like a very recent trick to make training GANs more stable. Okay, so with those 3 together, that makes the loss of the generator better. And then the discriminator loss is a lot simpler. It's just, it gets penalized for saying real images are fake or fake images are real. Okay, so now I can talk about some of the experiments they recorded in the paper. So one thing I should say is that evaluating GANs is a very hard problem. If you think about like the adversarial network, the adversarial nature where the generator and discriminator are both trying to learn at the same time, it's very hard to see how they're doing. I mean, it's easy for just looking at photos for humans to say like, this is a face, this is not a face, but it's hard to like get an algorithm to do that for us. Like, how realistic is this face? But there are a lot of attempts to do this. So this paper uses like 3 of the recent 3 of the recent evaluation metrics for GANs. And they also just use like a plain user study where they like ask a bunch of people to evaluate like how good these spaces are. Okay, so I'll just give a little bit of an idea for one of the automatic metrics, the FID score. So basically you have the distribution of your real data and then the distribution of the generated data. So that's like this graph here where the blue line is the real distribution and the red line is the fake distribution. And you want to just see how far apart these distributions are. The crocheted distance is sort of like the maximum at any one point of the difference of the distributions. Also, another technique people use to evaluate GANs is to not look at the distribution of just the input images, but use yet another neural network and look at the difference in the distribution when we use this neural network on the synthetic data and the real data, and then look halfway through at the embedding, and then look at the difference in the distribution for halfway through the neural network. Okay. And then, yeah, like I said before, they also did an experiment where they asked a bunch of people, they gave them 3 images of faces, 2 of them are real and 1 of them is fake, and they say, tell us which one is fake. Okay, so they compared their results to the 2 algorithms I mentioned earlier, X2Face and Pix2Pix. And the surprising thing is that their results are actually not so great on the automatic metrics like FID, but they got really good scores for the user study. So it's pretty interesting. So like the bold numbers are the algorithm that's the best, and they only get the best for the user studies. So they did experiments on 2 data sets. So the first half of this image, the top half, it's a much smaller data set. So the algorithms don't do as well, like the scores are worse. And then that's the data set they use to evaluate. And then they also use like a huge data set only for their algorithm, just to see how good their algorithm could do. And the really interesting thing is this number right here. So remember I said the user study is like they get 3 photos and 1 of them is fake. They actually get a perfect score for the realism. So the result was 33%, which means that people couldn't tell the difference at all. They were just randomly guessing which image was real and which was fake. One more thing, so you might have noticed they have like 2 different algorithms, FF and FT. So they had 2 different ways of running their algorithm. One is like a simple way, and one is the more complicated way. The simple way is FF, which is feed forward, and that's just like, as I described earlier, they just train a while and they just chop off the discriminator and like use the generator to generate images. And then the second algorithm is called fine tuning. So this is a much more complicated method, or a fairly complicated method where they actually do more training on just the new images before. So it's a way of like, it's a technique to fine tune generative models where you get your like 1 or a few images of the person you want to generate, and then you enter another training phase to try to really fine tune the weights of the network for that one person. And so that's how they got their best results. Any questions about this? Okay. So this is just a couple more examples of famous photos that they were able to make pop. I mean these are like really interesting videos. I don't think the algorithm is completely perfect. As you can see, like sometimes the hair gets a little messed up when the person's moving around. So this is a really compelling algorithm, but I don't think it's like in a perfect state yet. It's still we can tell the difference when, especially when people move around. Okay. So now I'll just wrap up. So this is the first work to report very high realism just on a single image. There's a little bit of things to improve on in future work, like the model can only take portrait style images, and also right now there's nothing in the model to support like which way the person's looking, their eyes. So they do like the face landmark, but they don't actually do gaze estimation. And also it's like not perfect with hair and like neck and upper body. So there could be some future work there. And then we might think like, what does this algorithm mean for like the current state world? So there's a lot of ethics that goes into research like this. Maybe I can just mention, so a common question is like, will we ever be able to tell what's real or not again? Like it could soon be very easy to generate completely fake videos. Even if like some politician, there's a bad video about them, even if it's real, they can say, oh, that's fake, like that was generated by an algorithm. So how will we ever know like what's real and what's fake? So some people might say like we're screwed, but there's also like, you might also say that machine learning can also help us decide what's real and fake. So like just as when I was explaining earlier about GANs, where at the end of training you chop off the discriminator and just use the generator. If you want to tell apart real and fake images, you might train a GAN and then chop off the generator and then use the discriminator to tell what's real. So that's just an idea of how we might, in the future, how we might be able to tell apart real and fake images and videos. Okay, so that's all I have, and I can take any questions you guys have. Yep.
Did you consider adding in some measure of interframe consistency into the loss function that might give you slightly smoother action in the output?
Yeah, so it's interesting. When I was reading their paper, it sounded like at training time they only took, so I know I described it as like a 9-second video, but they actually just randomly sampled images from the video. Then like tried to predict another random sample. So I think they're not actually learning the whole video, they're just trying to learn like you take a pose and you take a photo and then you output the photo in that pose. And then the way they make videos is just concatenate a bunch of those together using the landmarks that like are in the. So you're right, I think to make more like streamlined videos, that's a really good